All right, so this next problem has to do with conservation of energy. Specifically, you have been throwing a book off a cliff that gives it some amount of kinetic energy and some amount of potential energy initially. Then it falls 80 meters and ends up with just kinetic energy. So we can set up our energy balance. So we have energy initial, so potential energy. Let me make that smaller. We have potential energy initial plus kinetic energy initial plus work minus loss. I'm just going to say those are zero because we're not talking about any air resistance or friction or anything like that. So we're going to assume no work, no loss. And that turns into kinetic energy at the bottom with no potential energy. So that gives us that mgh initial plus kinetic energy initial, 1/2 mv squared initial is equal to 1/2 mv final squared. And then all you need to do is plug in the numbers that you're given. So I think one of the common mistakes here was that people plugged in the x component of velocity because we're so used to dealing with kinematic equations that it's natural to separate the x and the y components. But in this case, we're dealing with a transfer of energy, and any energy that's going into the x and the y direction is coming out as x and y velocity as well. So this is an important distinction to make. Anything at an angle still has the same amount of kinetic energy as its net velocity. You don't have to calculate kinetic energy in the x direction or in the y direction. So you just plug in your numbers. So this is going to be, well, we can cancel out the mass first. So 9.81 times 80 plus 1/2 times 30 squared is equal to 1/2 times the velocity squared. And then you just solve for velocity. Velocity final is equal to 49.7 meters per second. Fairly straightforward problem once you realize that the initial velocity that you're using is 30 meters per second.